All right, we're going to start with question 11.15a. We're starting with the secondary alcohol, and we want to make a primary alcohol. And I think that probably one of the best ways that we know to make a primary alcohol would be to have this alkene as our starting material. So like this. And for that, we would just do the anti-Markovnikov addition of water across that double bond. Well, now the question is, how do we get from the secondary alcohol to this alkene? Can anybody suggest some place to start here? Just what might be a good set of reaction conditions to kind of kick the whole thing off? Because the hydroxyl is not a good leaving group. If we were to just treat that with concentrated acid, if we just treated this with sulfuric acid and we heated it up, that would make the Zaitsev alkene, which isn't what we want. So that wouldn't be very helpful for us, would it? So I think a better option would be, so we wouldn't want to use oxymercuration, demercuration, because that is something that we would use an alkene as a starting material for, right? That would be if you had, let's say, if you had this alkene, then you could use oxymercuration, demercuration to make the secondary alcohol. So I think a good idea would be to start with converting this into a good leaving group. So let's treat it with tosyl chloride and pyridine, and that will make the tosylate, which is a good leaving group, right? We have the OTS, right? So again, what am I doing here? I'm taking something that's a poor leaving group, and I'm converting into something that's a good leaving group. Now I've got two types of beta protons, don't I? I've got my alpha carbon, which is this one here. Then I have beta protons on this carbon, and I also have a beta proton here, but I want to pull off the one on where the blue beta is. So I want to pull off one of these protons right here. How am I going to do that? For that, I would use a non-hindered base, right, to get the Hofmann alkene. And so I'm going to treat it with something like potassium T-butoxide. So let me just zoom back out here. If I take this and I treat it with potassium T-butoxide, we could even draw out the entire Lewis structure for fun and practice our mechanism. So if I put in the blue beta proton like this, what's going to happen? It's just an elimination where I rip off this proton, I make the double bond, and I lose my leaving group. And that would give me the Hofmann alkene, and that's the one that I want in order to do the hydroboration oxidation. So I would treat this with borane and THF in the first step, and then hydrogen peroxide and sodium hydroxide in the second step. So overall, it's what? How many steps? We've got 1, 2, 3, 4. So 4 steps for that synthesis. Let's try the next one where we're making a methyl ketone, right? We have a methyl ketone right here. And whenever I see a methyl ketone in organic chemistry, I always start thinking about an alkyne, because I know that if I had this alkyne, right, if I had this alkyne and I did a Markovnikov addition of water across it, that would give me this enol. I'll draw it out here quickly. That would give me this, son of a gun, this enol, which would undergo tautomerization to give me the methyl ketone, wouldn't it? All right. So now I'm, wondering, well, how am I going to get from a double bond to a triple bond? There's no way to do it directly. But we've seen this a couple times today, that if you started with, could anybody tell me what reaction conditions you might want to start with here? There's only one option. Can anybody make a suggestion of a first reaction to take that alkene and start the path? Yes, absolutely. Bromination. Perfect. So if we brominate this, right, that's going to give us the vicinal dibromide. And we've seen this several times today, that we can take a vicinal dibromide and we can convert it to the alkyne directly. Right, what do? We treat it with excess sodium amide in the first step, and then we treat it with water in the second step. and that's going to give us the desired alkyne. So oops, there we go. And then the last step is just going to be a Markovnikov addition of water across that triple bond. Well, how do we do that? We've only got one way to do the Markovnikov addition of water across the triple bond. We use an acid, sulfuric acid, in water, but we need something to spruce up the reaction conditions, and that is mercuric sulfate. Mercury to sulfate, and there you have it. And again, it proceeds through the enol, which undergoes tautomerization to give us the ketone. I find it helpful sometimes to write out those intermediates. All right, I wanted to also take a look at question 11.18, which I think is another good synthesis problem, or has a bunch of good synthesis problems. Okay, 11.18. First one's got a carboxylic acid, so let's write this down. So this is 11.18, right out of the textbook. So we're starting with this compound. This is 3-methyl-1-butene. We get a total of 5 carbons, and then we're making this compound, which is 2-methylpropanoic acid. But anyhow, the name isn't important because we haven't covered carboxylic acid nomenclature. But first thing I noticed is that you only have 4 carbons here. Okay. Another good news here is that we don't have many ways to make carboxylic acids, do we? Okay. Really, the only option that we have would be to start out with this alkyne, right, which has a total of 1, 2, 3, 4, 5 carbons, and then we would treat that with ozone in the first step and then water in the second step. So not only will we get this, we would also get CO2. That's neither here nor there. We're interested in organic compounds. So then the question becomes, well, how do I get from this alkene to this alkyne? Well, I think you know the answer, right? It's something that we just discussed. We would take it and we would treat it with bromine first to make the vicinal dibromide. Remember, vicinal means nothing more than neighbors, right? These 2 carbons are next door neighbors. So you have a bromine on one and you have a bromine on the other. So that's just a sassy word for next door neighbors, right? Vicinal. Then we do the double elimination to make the alkyne. Let's try that again. This is probably maybe our 10th time that we've done this reaction today. So excess sodium amide followed by treatment with water. That gives us the alkyne. There we go. And then the last step is going to be treat it with ozone. And the second step is to treat it with water in our ozonolysis. There you go. All right. So, I mean, you know, something that everybody here is aware of is that some of the reactions that we learn in organic chemistry have just like one reagent, right? Like bromination, Br2, that's just a reagent and it's a reaction by itself. But other reactions require more than one reagent, right? I think a good example would be ozonolysis, right? If you just treat it with ozone, well, that doesn't get you to the carboxylic acid, does it? So it's a 2-step process, but overall it's considered one reaction. You know, it's kind of the way I think about it. Anywho, let's try B, which involves another carboxylic acid. So we're gonna have to do some more alkyne chemistry. So this is 11.18 B. So we're starting it with this compound. This is 2-methyl-1-bromopropane, and we're adding a carbon here, aren't we? So let's see, end up with this compound. This would be 3-methylbutanoic acid. So let's see, we've got a total of 4 carbons in our starting material, and we've got a total of 5 carbons here. Okay, well, let's do some retrosynthesis. I think that's where we should start, and we would have to say, well, if we wanted to make this compound, then we would have to have what as our starting alkyne? We would want to have this compound. And now, if we think about going from here to here, from the primary alkyl halide to the alkyne, we can see that we're adding these 2 carbons to the molecule. Well, how would we do that? We would just use acetylide. So that's what we're going to do. We're going to treat it with sodium acetylide. So let's do that. So we're going to treat it with sodium acetylide, which you can just assume is a reagent. Okay, that would do an SN2 reaction like this, and that would give us the desired alkyne. Like this. So now we've got 1, 2, 3, 4, 5, 6 atoms in the carbon atoms in the molecule. So now we do the ozonolysis, right? First step is to treat it with ozone. Next step is to treat it with water. And like somebody is saying, you know, since this is a terminal alkyne, if we cleave this bond, not only do we end up with the carboxylic acid, but we also end up with carbon dioxide. But since carbon dioxide is a gas, it's not going to be isolated from the reaction mixture, right? It's a gas. It's just going to bubble out and go up into the atmosphere. So we just leave it out. We don't write it as a product. Can you? Absolutely. You could write it as a product, but the reason it's not included here is because it just goes up the smokestack, so to speak. Does that help? Or does that answer the question? All right. In the next one, we have the same primary alkyl halide, and we're taking it and we're converting it into an aldehyde. And, you know, again, this is one of those situations where we don't have many ways to make an aldehyde, do we? Right? In terms of what we've learned in Organic Chemistry 1, what's a way that we could make an aldehyde? We'd have to have an alkyne, or we could have an alkene and we could do ozonolysis on it, right? Like what if we had this alkene, just thinking here, if we had this alkene, right? And then maybe if I drew it like this might be more helpful. What if I drew it like that? Right? If you had this alkene, where you have the hydrogen here, and you treated this with ozone followed by DMS, right? That would cleave this bond here. Okay, so that would give it the aldehyde, and then now I think it becomes a little simpler. You have to go from here to here, so you're adding a total of 2 carbons, right? You're adding these 2 carbons to the molecule, which you could do the same thing that you did in the last problem. Just treat it with sodium acetylide. Okay, so let's do that like this, which is going to do an SN2, and it's going to give you this compound. So now we've got our triple bond like this, and then we could reduce this any number of ways to the alkene. Right? You could use sodium metal reduction. Let's try that. You could use Lindlar's catalyst and hydrogen. That would work too. And then in the last step, all we do is we take it and we treat it with ozone, followed by DMS, like that. So it's only a total of what, 1, 2, 3, 4 steps total. So it's not too bad, but I think this one, personally, I mean, you might feel differently than I do about it, but I think this is a really good candidate for retrosynthesis. You know, because we're adding only 1 carbon to the molecule, so I think it'd be wise to solve this by retrosynthesis and start it with this alkene like that. All right, let's try the next one, 11.18D. So this is 11.18D. So we're starting it with butane, or sorry, isobutane. So not a lot of options there. And we're converting it to this alkene, which is 4-methyl-1-pentene. All right. So we're adding 2 carbons to the molecule, aren't we? Okay. Well, if we think about this in terms of retrosynthesis, I mean, if we had, and I'm kind of taking a couple steps back here, but if we had this alkyl bromide and we had acetylide, right, that's not going to give you that compound, but it's going to give you the analogous alkyne, and then you could just reduce it, right? So then the question becomes, well, how do I get from isobutylene or isobutane to this alkyl bromide, right? Well, the first step, the only option we have is to treat it with bromine and light, which gives us this compound, 2-bromo-2-methylpropane. And then if we treat this with a base, we can make isobutylene, which is the compound I had in my brain when I was thinking about. Right, so for that, we can treat it with any number of bases, but this is a tertiary alkyl halide, so we're not going to get any substitution. So we could even just treat it with sodium methoxide, and that's going to give us this compound. So this is isobutane, and this is isobutylene. Okay, it's just the names, common names that we use for these. And then we can do an anti-Markovnikov addition to get to this primary alkyl bromide, can't we? We would take that, treat it with HBr and peroxides, and that would give us this compound. Oops, I added a carbon there, didn't I? There we go. All right. So now if we treat this with sodium acetylide, that's going to do an SN2 and give us this compound. And then in the last step, and I'm kind of running out of room here, but we could just treat this with sodium and liquid ammonia, or we could treat it with hydrogen and Lindlar's catalyst. Either way is going to be perfectly reasonable.